Click the bell icon to get latest videos from Ekeeda.
Hello students, welcome back to the subject of Machine Design 1. We are right now learning about the crane hook design. In today's session, we are going to look at the second numerical based on crane hook design. Let's look at it. So you can look at the screen and the problem statement along with the diagram, schematic diagram is given. They say that a curve bar which is subjected to the given load. So it's a form of crane hook which is given to us. Its material property, yield strength is given. Factor of safety is mentioned. We need to find out the diameter D of this particular cross section. So we can see that cross section is basically circular in nature. This particular value has been given, which is equal to 4 times the diameter D. This is nothing but a Rn value, based on which we can figure out the inner radius and outer radius. The load of 1 kilonewton each is given, so that this can be its hanging position and this can be the position where the load can be attached. Let's proceed. Let's consider the cross section XX at any point where it is going to be circular only, with the diameter D. We have been given that R, which is the nominal radius, which is equal to 4 times D. So the inner radius is quite obvious, is the outer radius minus half the diameter, which is radius. So it comes out to be 3.5 D. On the same lines, the outer radius can be found out using the mean radius plus radius, which is equal to 4.5 times D. Now, from PhD data book, we can easily figure out for the circular cross section, the nominal radius R can be given by this particular formula. Let's substitute the values. After evaluating this expression, we will get the value of Rn equal to somewhere around 3.9843 times the diameter D. To move about ahead of this, let's figure out the expression E, small e, which is nothing but the radius, which is 4 times the diameter D, minus the recently found out value, millimeter. So that is how it's very small eccentricity that is obtained in this particular case. To move ahead with HI value, let's consider Rn value, which is 3.9843 times diameter D, minus the inner radius, which we have found out is 3.5 D. The answer somehow comes out to be last but not the least is the area of cross section. We know that the area of cross section of this particular thing is pi d square by 4 itself. Using all of these parameters, let's move ahead for the design aspect. Now we know that the bending stress may occur, and for that bending moment is required. We know that bending moment will be given by the force value into the radius. The force value have been given is 1 kilonewton, that sum ups to 1 into 10 raised to 3 into radius R. So radius R here is 4 times diameter D. So this is what the bending moment that we have obtained. To move ahead, let's find out the bending stress. We know that the bending stress will be maximum at the inner fiber, and that's why we should consider the inner aspect. So that is how bending stress on inner side is sigma Bi. This is the formula that we have. Let's substitute the values. The value is in Newton millimeter, of course. the value of HI somehow is equal to the area of cross section, the eccentricity, and the inner radius, which is 3.5 times dt, are the important factors that we have. So with these factors, let's evaluate this expression and get sigma bi value in terms of diameter d divided by d square. Since it is a stress, the value will always be in Newton per millimeter square. So here unknown being d, we have to put the expression in terms of d only. Let's move ahead and consider direct stress also, because that is the second component of stress. In that case, it becomes so this expression also in terms of d we have obtained. Let's combine these two expression whose units are again same. So considering their superimposition, we can say the total stress will be given by divided by d square plus 4 into 10 raised to 3 divided by pi d square. Now we have been given the yield strength is equal to 400 and the factor of safety associated is 3.5. If you look at or you can observe it very carefully that only unknown that we have here is the d square, and therefore taking it common we will get and therefore evaluating this expression we obtain the value of d is equal to somewhere around 20.10 millimeter. So that is what the value of diameter is, which is expected based on this particular combination, which is going to be a safe dimension. So this is how we have demonstrated two different numerical. In the last numerical, we have found out the load carrying capacity based on the given design aspects. In today's problem, we looked at it in different angle and we found out the dimension which is required for the given specifications. So there we end with the design of crane hook. In next session, we'll be looking at some other component where static loads do act. Thank you so much for watching this video. If you like this video, please subscribe to Ekeeda. Thank you.